Hi, everyone. Today we are talking about moment of inertia. We've mentioned this a little bit before in the chapter, but today we're going to go more in depth. First slide asks us, do Newton's laws work in angular world? So what we're going to do is we're going to start with F equals ma, and we're going to modify that equation to work in angular world to see what that's going to look like. So first, I'm going to give you the F equals ma, and then every time we make a change, I'll give you the reason that we're making that algebraic change. Okay? So first, we want to clarify that this is a tangential force using tangential acceleration on some particle mass, right? To clarify that this is a force tangent to the radius and the acceleration also tangent to the radius. Like we talked about before, tangential acceleration is the XVA, the traditional acceleration that we talk about in linear world. Now, first, what we're going to do is multiply by r. Multiplying by the radius will give us ft times r equals mat times r. Right? Now, we do want to recognize that if this is tangential force, right, that we're assuming 90 degrees. That means that torque is going to be ft times r, right? Because we're assuming sine 90 being 1, that'll just go away. So now we have torque equals mat times r. Now we've kind of run out of things to simplify, so we will take at and we'll actually throw in some more variables. Acceleration is alpha times r, so now we will actually say this is alpha times r squared. And now, if we are doing this to an object, right, because torque is usually done to an object to rotate an object, we now have to consider all mass in the object. Consider all mass in that object, so this becomes a summation. Okay, you've got summation of torque equals the summation of all mass times its alpha times r squared. Right? However, here is where we introduce our new concept. I, which is the symbol for moment of inertia, is the summation of all particles' mass and their radii squared. So now this becomes net torque equals I alpha. That is Newton's laws in angular world, right? We already said that torque is analogous to angular force, right? This is why, because when you look at F equals ma, it actually translates really well to angular world. If you say that torque is kind of like the angular force, we already know that angular acceleration is literally the angular version of acceleration. And now we're going to say that number 2, explain what is the equivalent of mass in angular world. Moment of inertia is your angular mass, right? It's kind of, moment of inertia implies that it's kind of like the measurement of resistance an object will give you to move it, right? Kind of like how mass or inertia is just kind of like you're just measuring how much resistance this object may take to change its motion, right? To either give it a velocity or to change its velocity, either direction or speed. So now we have angular force, we have angular acceleration, now we have angular mass as moment of inertia. So, and now we get to the puns, right? I'm so mad I could shake a stick at it. So the idea behind this is to actually grab a meter stick in class and try to rotate it holding it in the middle, right? Let me go grab one real quick. I don't know how this is going to show up on video, but we'll see. 1 second. All right, so I've got a meter stick, right? If I hold it at 50 centimeters, right, and rotate it, not difficult. I am using just my forefinger and my thumb. It is a relatively simple task. However, as I move that further along, so I'm going to move out to the 30 mark, actually takes quite a bit of effort. Move down to the 25 mark, considerably more effort. Now down to the 15 mark. I almost need to use my middle finger to assist. It's getting a lot harder. Then if I get down to the 5 mark, if I put my forefinger and my thumb at the 5 mark, it's actually harder. I have to move my thumb out to about 7.5 or 8 to really get the torque I need to actually move this thing back and forth. And then if I move it all the way to the end, it's considerably more difficult than if I just hold it in the middle, right? So as you get further and further from that middle, it got harder and harder to rotate. Right? So number 1 says, where is the stick easier to rotate? In the middle. And we're going to call that middle center of mass, right? So it is easier to rotate at center of mass. Now, so is moment of inertia a constant for a given object in all situations? That answer is a profound no. Okay? That is not going to be constant. It's going to change. And what is it going to change with respect to? Well, it's obviously depending. It depends on the axis of rotation. Now we know that it has the equation, okay, I equals mr squared, right, or the summation of all mass and their radii squared. Now if you increase the masses, obviously you'll increase the moment of inertia, but if you increase the radius, right, increase how far you are from that axis of rotation, then you are going to increase the moment of inertia, which is going to take more torque to give you acceleration, right? Just like if you increase the mass of an object, it's going to take more force to give it acceleration. So it depends on that axis of rotation, where that object is rotated about. That's going to determine the strength of the moment of inertia, right? The value of the moment of inertia. Now, what is r in the equation? Okay, R, like a lot of our equations, has a very specific definition, right? So when we have torque, right, being Fr sine theta, that R, right, is that's the radius from the axis to the force. Okay. Now for moment of inertia, if that is mr squared, this radius is now different also. This is the radius from the particle or from the mass to the axis, right? So it depends on where that particle is on the object and or where that particle is in the system, right? So the most common way that we introduce these things is by particle masses, right? We did the same thing for center of mass. Here are some particles, find the center of mass. Then we used calculus to use solid objects. We used area, right, to do complex center of masses for areas. And they're silly center masses. So we'll go to a particle problem first. Okay, 1019, a moment of inertia. Okay, like center of mass, we have non-calculus and calculus ways of finding moments of inertia. So first, we want to calculate the moment of inertia for this system of attached particles rotating at the drawn axis. Okay, we're assuming that that rod is rigid and massless. So we want the moment of inertia. So the moment of inertia is the summation of all masses and their radii squared. So let's take all of the masses. You've got 2, 3, and 4, right? I'll get these in order, right? Let's just call them mass 2, mass 3, and mass 4 for simplicity. Mass 2 is 2 kilograms. Mass 3 is 3 kilograms. Mass 4 is 4 kilograms. But their radii are different, right? Radius for 2 is -2 meters. Radius for 3 is -4 meters. And radius for 4 is +3 meters. So, as we sum these up, right, we're going to take m2 r2 squared plus m3 r3 squared plus m4 r4 squared. So you've got 2 kilograms times -2 meters squared plus 3 kilograms times -4 meters squared plus 4 kilograms times 3 meters squared. So here we've got, what is that? 2 times 4 plus 3 times 16 plus 4 times 9. And that should come out to 92 if you put that in your calculator, or if you just know those numbers. 3 times 16 might be a little bit harder, but 92. Okay? Now, what is the unit that we're using for all of this, right? So we're taking kilograms and squaring meters, so this is 92 kilogram meters squared. That is moment of inertia's unit, kilogram meter squared. Now, that's the moment of inertia of this system of particles if they're rotating about the x-axis, right? It tells us y is the distance from the x-axis, right? So, letter B says how much torque is necessary to accelerate at 2 per second, right? 2 radians per second squared. So if we know, if we want torque, we know I and we know alpha being 2. Okay, we'll take 92 kilogram meters squared times 2 seconds to the -2 power. So you multiply that by 2, that's 184. And that is kilogram meters squared per second squared, which is a Newton meter, right? I guess I should put my numbers there. That is 184 Newton meters. A Newton being a kilogram meter per second squared. Multiplied by a meter, you get kilogram meter squared per second squared. So that's the torque it takes to rotate this, actually to accelerate this system of particles at the rate of 2 radians per second squared. Now letter C asks, would the moment of inertia stay the same, increase, or decrease if you rotated at an axis that is parallel to the x? Okay, so we're parallel to the x here, but we're going to go through the 4 kilogram particle up here. Explain or calculate to justify your answer. We're going to do both. Right? So let's explain first. Use a different color. So if we have I equals the summation of mr squared, right? If we rotate about that 4 kilogram particle, now those 4 kilograms are negated from our moment of inertia mass, because R4 now becomes 0, right? So now we're not going to include that particle. Any particle along the axis doesn't take any effort to rotate because it's not rotating, it's spinning. It's very different. So we are losing 4 kilograms out of this mass. So you would think that since we lost mass, we're going to lose moment of inertia and it should decrease. However, we are also extending the radius of our particles. Okay? We extend the radius of all of that. So if you change the mass, but you change the radius, a change in radius is actually going to be amplified, right? Because of this exponent. Because of that exponent, you're going to have a greater change in radius, or I guess radius will have a greater change on moment of inertia than mass. So here I would argue that, right, we are losing 4 kilograms off of the mass, but we're increasing all of our radii by 3 and then squaring them. So that is that is most likely going to cause an increase, right? That's just going to make sense that if you decrease mass, but then increase radius, that's going to weigh more, right? That's going to have a stronger effect. So now let's do the math, right? It said explain or calculate. Let's actually calculate it. Okay? I will equal m2 r2 plus 3 squared plus m3 times r3 plus 3 squared. And then m4, r4, they're negated because the radius is 0. So we'll say that m2 is 2. The radius is negative 2. But now we're going to increase that by 3. So that really should, I guess, be minus 3, right? Because we're actually, yeah, let's say minus 3. Because we're increasing their length. Actually, you know what we could do? That's not very appropriate math. What we can do is say the absolute value of their radii plus 3. It's getting squared, right? So we will say that this is going to be 2 plus 3 squared plus the mass of 3 times its radius, which is absolute value of 4 plus 3, so that'll be 7 squared, right? So if we do this math, you're going to have 2 times 25 plus 3 times 49, right? 7 squared. So this will come out to 197 kilogram meters squared. So that is a big increase from our 92 to 197, right? We are over doubling our moment of inertia there. So moving that axis, yes, it caused a decrease in mass, but the increase in radius by moving that axis actually caused an increase in our moment of inertia. Okay? And we were able to explain and calculate that. Now, for our last slide, we have 4-point masses. Okay, we've got a system of 4 masses attached to a rigid frame of negligible mass, as shown in the diagram. Okay? The 2 capital M's here are going to be equal in mass. The 2 lowercase m's are going to be equal in mass. A's will be equal and B's will be equal in distance. Now, letter A says first, why does the frame being rigid and massless matter? Well, we know that moment of inertia relies on 2 things, mass and radius. If it's rigid, rigid means the radius won't change. Radius stays constant. If it's not rigid, that means that the radii might change as this object rotates, or just as it sits still. If it's massless, okay, that means that we don't have to consider the mass of the frame, right? It looks like, was that a rod of some sort? So we don't have to consider the mass of the rods. We just need to worry about the particle masses, okay? So here, you can ignore the frame's mass. Then you only calculate particle masses. So that's going to be really important. It's got to be rigid. It's got to be massless, because if it's not, then the M or the R could change at any second, and that would throw a whole new wrench into the problem, right? So good thing it's rigid and massless. Now, suppose the frame rotates along the y-axis as shown, right? Here we see that it is rotating about the y-axis. So, like we just said in the last problem, that means that this mass and this mass we're not going to factor in because their radius would be 0, right? Their distance to the y-axis is negligible because it's 0. In our math, it's going to go away. So calculate the moment of inertia. So we'll say this is moment of inertia for part B. You've got mr squared. So you've got big M times a squared plus big M times a squared. Okay, so you have 2 ma squared. Right? So that is our moment of inertia for part B. Okay, 2 ma squared. We're just dealing with symbols for now. Now, if we want to look at what happens if the frame now rotates along the rotates at the origin on the z-axis, will the moment of inertia increase, decrease, or stay the same? Calculate and explain, or explain. We'll do both. So the z-axis, right, is coming right out of the origin, and imagine it's either coming out of the screen or going into the screen, right? That is the direction we're talking about when we talk about the z-axis. So if it rotates about the z-axis, I see. Okay. That means that so ma squared and ma squared, the ones that we just factored in, they're not going to change. But now we're going to consider 2 more masses and 2 more radii. So that will cause this to be greater than the previous one because we're adding mass and radius. Now we're considering more particles. That's going to increase, right? So now we can actually see what that would be. We've already got 2 ma squared. Then you would have, what is it, little m, little b. So you got little m, little b squared plus little m, little b squared. So now you've got 2 ma squared plus 2 mb squared. And it doesn't matter the values of the m's, a's, or b's. When you compare these two, obviously increasing the mass or in the radius by value b, that's obviously going to cause an increase. Right? So changing the axis of rotation, like we talked about, is very important to moment of inertia, right? Moment of inertia relies on and is dependent on the location of that axis of rotation. In our next video, we will continue on talking about moment of inertia, but instead of doing the summation, we're actually going to move on to calculate moment of inertia using calculus.